In this lesson, we're going to be looking at several different equations that deal with velocity. Before we do that, though, let's look at the top of our packet, and we have a section called Activate Your Brain. Would you please warm up by doing these problems? Go ahead and pause the video, complete the parts A, B, and C, and then turn it back on to check your answers. For part A, 32 millimeters is going to be 3.2 centimeters, which is 1.26 inches. That was from chapter 2. Part B, what's the equation for average velocity? This is from the previous lesson, and the equation is bar v equals delta x over t. Remember that the bar refers to average, and the triangle in front of the x is the delta, which is a change in location, otherwise known as displacement. Letter C, when have you calculated how long a trip should take? Perhaps you've done some sort of a longer trip where you try to figure out when you will arrive at your destination. These equations that we deal with today are going to be along that lines. So today's goal: to learn how to use equations to calculate velocity, distance traveled, or the time of travel. The big idea here is that the equation for average velocity can be used to calculate things besides velocity. The equation that has velocity in it includes other things like locations and times, and we can solve for the time or solve for locations. Number 1, rewrite the velocity equation to include the initial and final locations. So we start off with, here's our basic velocity equation, bar v equals delta x over t. And instead of this delta x, we're going to rewrite this equation with our x sub f and x sub I. Remember that delta x is equal to the final thing minus the initial thing. And so we change the top of our equation to be that. The t on the bottom stays the same. The bar v stays the same. It's just the delta x that's changing. Part number 2. Rewrite the velocity equation to have the final location by itself. So here, x sub f is the final location of the object. We want to get this variable by itself. Now, I realize that there are two letters here, the x and the sub f, but it's still considered just one variable. The f is just making us be focused on what kind of location it is. So anyway, to get this x sub f by itself, we're first going to multiply both sides by t. That will get me bar v t equals x sub f minus x sub I. The t here and the t there cancel out. Okay, now we're still trying to get this x sub f by itself, and so we need to add x sub I to both sides. We'll get then bar v t plus x sub I equals x sub f. We have the x sub f all by itself now, which is what our goal was, but it's a little bit more traditional to have the single variable on the left-hand side. So I'm going to flip everything backwards. X sub f equals x sub I plus bar v t. And that's the end for question number 2. We're going to use those two equations that we derived here to solve problems like numbers 3 and 4. Darrell Green, one of the fastest pro football players, started out on the 10-yard line. He ran at an average speed of 8.31 meters per second for 4.4 seconds. Where did he finish? When you do story problems like this for this chapter and for many chapters to come, the first step is going to be to draw a picture. And so there's my guy. You don't have to be fancy with it. Stick figures are just fine. You can even just do rectangles if you want to be even more rudimentary. Okay, now once we have the object that's moving, we need to include the coordinate system. So I'm going to put it back here. I'm going to put it behind him because it says that he started on the 10-yard line, so that seems like it's being measured according to the goal line. And so I put the coordinate system with the 0 at the 0-yard line, which seems reasonable. And we're going to have the traditional way of having positive to the right. So this is my coordinate system right here. Okay, now labels. I have to take all the information that I know from the story problem and put it on the picture here in some way. So I'm going to put x sub I for the initial location equals the 10 yards. Have an arrow showing his motion, and the average velocity is 8.31 meters per second. That's all that I know. Next, what do I want to know? We know one more thing. We know the time is 4.4 seconds. Okay, now since the time is the time of the motion, I put that by the arrow here and the velocity of the motion. Okay, now I have everything that I know in the story problem. What is it that I want to know? I want to know x sub f, the final location. So I put that on my picture with a big question mark. That will help focus my attention. Okay, now I have everything that I know. I have what I want to know. What equation will relate the desired variable with at least some of these things? There might be some extraneous information here. We may not use all of this information. But what equation has x sub f? Well, we have a couple of different ones to choose from. I'm going to use this version that has the x sub f by itself. Okay, next, substitution with the units. Before I substitute in my numbers, x sub I for 10 and 8.31 for the v, I need to make sure that all of my units agree. And I can see that they don't. I have yards here with the initial location, but my velocity has meters. So I have to change one or the other. I'm going to end up changing the velocity to be yards per second, and that's 9.09. All my other units are fine. I have seconds here, and I have seconds there. So we can now substitute in. So my x sub f stays the unknown. The x sub I is the 10 yards. The average velocity is 9.09 yards per second. The time is 4.4 seconds. Now I can do my algebra. When I multiply here, I can see that my seconds on the top and bottom are going to cancel out. So I'm left over with yards in this term and yards here. Those will be able to be added together just fine, and I'll come up with my final location in terms of yards. And the answer is 50-yard line. So what Darrell Green was doing here was what's known as the 40-yard dash, and he has one of the best times ever. Question number 4. The world's fastest unmanned airplane, the X-43 scramjet, was launched from a B-52 bomber about 300 kilometers east of the California coast. It flew westward at a speed of 11,265 kilometers per hour. It crashed into the ocean 314 kilometers from the shoreline of California. How long did it fly? Now, just to throw in some extra trivia here, it was planned to crash. There wasn't anybody flying it. They didn't want to invest all the money in landing gear and remote control in order to guide the thing onto the airport. So they just aimed it out into the ocean and let it crash when its fuel ran out. So anyway, here we go with our picture. Here's the coastline of California. And since everything is measured in relation to the coastline, the initial location, the final crash location, is measured according to the coastline. Because of that, I'm going to have the coordinate system where the 0 is the coast. And the traditional setup of positives to the right, negatives to the left. Okay, that's our picture and the coordinate system. Let's throw in the labels now. The initial location is 300 kilometers on the east side, or the right-hand side, of of the coastline. So I have x sub I equals a positive 300 kilometers. My positive mark got kind of mixed in here with the picture of the airplane, but it's there. The final location is 314 kilometers on the west side of the coast. And in this picture, west, or to the left, is on the negative side of the coordinate system. So I have to include that negative sign here for x sub f. And then I have the motion here. I have an arrow being drawn showing which way it's going. The average velocity is 11,265 kilometers per hour. And that's going to the left, which is the negative direction. So I included a negative sign here on my 11,000. And what I'm looking for is the time of this motion. So I have t equals question mark. My picture is now all done. Let's look at the raw equation. What equation will give me time if I know these other things? Okay, we don't have many to choose from, but I'm going to use this equation, the same one as before. We're going to put in numbers for the x sub f, the x sub I, and the average v, and we're going to solve for the t. The t stays a variable at first. Now notice here that I could substitute in my numbers really nicely because all the units agreed. We had kilometers everywhere. So doing my algebra, I come up with 0.0545 hours. All of my kilometers are going to cancel out when I do my algebra. It's only the hours that are left over. Please make sure that you can do your algebra correctly so that those kilometers do indeed cancel out. Okay, line number 5. Ig. You may notice in the coming chapters that I have a lot of story problems dealing with two characters called Ig and Og. I won't bore you with how I got those names, but those are guys that I kind of envision being like the Three Stooges. They're not exactly the smartest guys in the pack. Anyway, here we go. Ig is flying his own homemade airplane. He starts off 1 kilometer north of his home and flies south. After 60 seconds of flight, he is located 200 meters south of his home. What is his average velocity? So let's draw a picture. I have the house. I have a very poorly drawn airplane here, and here's my coordinate system. So this is on the north side, looking like a map. North is going up above, and so I'm going to have positive being above. That's the traditional way of doing things. And now let's put in some labels. We have the initial location is 1 kilometer on the positive or north side of the house. The final location, I'll draw another airplane down there, is 200 meters, and it's on the south side, on the bottom side of the map, and so I have a negative sign here. Negative 200 meters is the final location. I can see right away that I have a difference of units here, kilometers and meters. And so I'm going to change that 1 kilometer to 1,000 meters right away. The airplane is flying from here down to there with a time of 60 seconds. We want to know what the average velocity is. So the equation that gives me average velocity could be this one. We could use the other ones as well. So I put in my numbers. For the x sub f, I'm going to put in the 200, and remember it's negative. For the x sub I, I'm going to use my 1,000 meter version so that the units agree, meters. I'm looking for the average velocity, so that stays a variable, and we use the 60 seconds for the time. Do your algebra, and you'll come up with an average velocity of negative 20 meters per second. Now that negative is not a mistake. Remember, the airplane is flying south. That's down on the map. Down on our coordinate system is negative. So the negative tells us what direction, and that's part of the velocity. Extra discussion. Please make sure you have this filled in on your notes as well. What do you do if you can use more than one equation to solve a problem? And that is oftentimes the case. You just use the equation that will require the least amount of algebra to solve for the desired variable. You choose the easiest equation, in other words. And that's the end of our lesson.